Hi, everyone. My name is Aaron Liu. I'm a second year PhD student at Stanford, well, technically going into my third year. And I mostly work on diffusion models applied to different domains, such as geometric domains, such as manifolds, discrete domains, such as graphs, or in this case, bounded domains in Euclidean space. And yeah, today I will be presenting our work, reflected diffusion models, published at ICML, with me and my advisor Stefano Erman. To start off, I'd like to give a brief recap of diffusion models to establish a common terminology and to also fill in any missing gaps for people. Diffusion models work by perturbing a input data distribution according to some stochastic process. And this stochastic process takes the form of a stochastic differential equation, such as the one given here. It's important for everyone to understand that f and g are both fixed and like pre-known and pretty simple coefficients. For example, f could be something like negative x, and g could be something like 1, and this would give us a OU process, given here dx is equal to this negative x dt plus dbt type of stochastic differential equation. And the magic mostly happens due to following a time reversal formula that we have for these diffusion processes. So in particular, we can reverse the diffusion process, which in principle would take us back from our noise to data. And we can accomplish this by following the reverse stochastic differential equation, which is given by this equation here. The only difference between this and our other forward stochastic differential equation, or the thing that we don't really know, is well, first of all, yeah, it's important to also understand that this is not a deterministic reversal, but actually a reversal distribution, which allows for sampling. And yeah, as I was saying, the only thing that we don't really know is this gradient log probability function here, which is also known as a score function. The score function is nice because when we try to model it with something like say a neural network, we don't have to actually constrain the score function in any way. So normally our probability distribution PT, we have some type of constraints. In this case, it has to be greater or equal to 0 at all points, and also has to integrate out to 1. So if we try to model a probability score, a probability function, we have this kind of constraint we have to place on our neural network. Whereas if we approximate our score function with a neural network, since a score is a general type of function, and it's pretty general, we don't have any of these constraints such as positivity or it doesn't have to integrate out to 1. In fact, we can model it pretty generally with a neural network and everything works out. And so yeah, the basic idea here is that we want to learn this score function in order to parameterize the reverse diffusion process. And how do we do this? Well, we can minimize the following score matching loss. This is what's called the score matching loss in the literature. The idea here is we take sample points from PT, and then at each sample point, we can parameterize the neural network as theta, which takes an input point x and a time step t. And then we try to minimize the sort of L2 loss with the ground truth score function given like here. So it's a very typical expected L2 loss function. Well, the issue here with trying to do this in practice is that this score function, we don't actually know it. So it's kind of it's a bit of a circular definition here because we want to learn as theta given our ground truth score function, but we don't know our ground truth score function. So this kind of messes it up a little bit. But we have this nice trick from mathematics. Basically, since our probability distribution PT, it decomposes as kind of you convolve it with this transition kernel PT of x given x naught. And we have this initial data distribution P naught x naught. We have this nice convolution. We can in fact write the above score function, score matching loss in this other form. Basically, we can just simplify it out using this convolution kernel to this other form. And the interesting or nice thing about this other denoising score matching loss function, which is given below here, the nice thing about this is that this gradient log probability of the transition kernel, well, this actually is, we know this in closed form, and it's derived from our forward SDE. So basically, we can actually learn our score function without having to know the ground truth score function, and we can optimize this relatively tractable loss function here. And so yeah, we can put everything together. So we start from noise, We follow the following generative SDE, where S theta takes the place of our ground truth score function, where we want S theta according to our like score matching loss. And then, once we follow it, we can generate samples by starting from random noise and iteratively following this SDE to generate like samples, like high dimensional samples, like images, for instance, as shown here. And another interesting thing that we have, and this is something that people use a lot in practice and will be important later, is we have this nice notion called diffusion guidance. Effectively, by Bayes' rule, our conditional probability distribution P of X given C decomposes like the ratios are the same as the probability distribution of X times the probability of C given X. And we can take a nice gradient log operation, and everything decomposes based off of linearity, and we get the following decomposition of score functions. So if we approximate the first value with a score network, so this is our ground truth score network that we learn, and then we have some classifier, this P of C given X. Well, then we can just take our pre-trained score network and our pre-trained classifier to generate samples conditionally without having to explicitly train for C. And in particular, we can also like do whole lot of nice like guidance type of stuff, which helps us generate better samples if that's what we're looking to do. And yeah, so this is like a pretty good mathematical theory, a pretty nice, well-encapsulated mathematical theory that like explains a lot about like diffusion models. But the issue is that a lot of problems can arise when we actually try to train our score models and when we actually try to sample from them. So in particular, like one of the main things that like people have noticed is that if you take our when you sample from this SDE, this generative SDE, you have to discretize like the SDE naturally. And a couple things arise. So first of all, the score network S theta, we can never learn it perfectly. Our time step is also like discretized. So instead of taking a continuous integration for an SDE, we have to take a discrete time step. And also our random like Brownian increments are well, in this case, they're discretized Brownian increments. These can be pretty random, which can also throw off your sampling process, like because it's just due to pure noise, pure chance. Well, when that happens, when we actually try to sample from our distribution, let's say we start off here, we take one step, another step, and so on. Eventually, we start heading into these low probability regions, basically. And for these low probability regions, the issue isn't so much that they're low probability, but the issue is more so that when we try to like learn our score network S theta, since everything is dependent on our like since we take expected values from our probability distribution, if we actually like go off and we like diverge to like a low probability like area, then we can't really learn this S theta accurately because the loss function does not penalize it for being inaccurate in these areas as much. And as such, when we actually do this in practice, what people have noticed is you actually get a lot of like blanking out of images. Basically, the issue is that the image like goes out of bounds a little bit and it keeps on going out of bounds. So when you actually try to visualize it, you get these types of blank samples. So the top set of samples, or this guided diffusion samples, is from a well-known GitHub repository, well-known paper from like OpenAI a couple years back. So the thing here is we just take their like pre-trained code, pre-trained models, everything. We just modify the code a bit to like do the actual sampling process because they have, as we'll talk about soon, a hack in order to make it work. But yeah, we take their pre-trained code base, pre-trained models, we try to sample. We get like 3 out of the 4 images are completely blank, and the last image we don't really know what's going on here either. So we can see that this phenomenon arises like a lot in practice. This also played a big part in the ImageGen paper from 2022, last year. Basically, for the ImageGen paper, the authors explicitly noted that like, yeah, if we try to like sample an astronaut riding a horse in this case, we try to sample from our model using this like our like standard sampling procedure, we'll end up that 3 out of the 4 images that we get are basically blank. You can argue that this has like kind of a arm and a leg here for like the third image, but like, yeah, 3 out of the 4 images are basically completely black, completely blank, and not usable in practice. And so you might be asking yourself, if this is the case, if it really is the case that we have this like divergent sampling phenomenon that occurs for diffusion models, Like how do people like make sure this, like how do people get the good images that work well in practice? And one of the techniques that people use, and this is like a pretty like well-known technique, is this idea of thresholding. And so the basic idea of thresholding, like we take the standard like discrete step that we worked with for our SDE, and we actually have a nice like interpretation of this discrete step through the lens of a VAE, or a variational autoencoder. Effectively, we have this like first part of the discrete step, and this is kind of like a VAE predicted mean. So this is like the mean of our VAE prediction. We also have like some VAE noise, basically, since our Brownian increment is like a normal distribution. This is like a kind of like a VAE, like we have a mean and a standard deviation, and like this works like as a good interpretation. And if we think about our our inductive bias for our like model. So we're trying to model images, let's say all the image pixels need to be between 0 and 255. This is a standard like constraint for images. We can rescale this to -1 to 1 as is done normally in practice. Well, if we want to like sample from like sample an image, and we have this nice idea of a VAE as a as a way to interpret the like discrete like SDE steps, then one thing that we can do is that when we start from our like SDE, whenever we go out of bounds of this image space in particular, so we take a VAE, we like go out of bounds for this VAE step. Well, that doesn't really make sense. So one thing that we should do is that one thing that we could do is that we could clamp all the pixel values to this -1 to 1 or 0 to 255 space, and then we continue sampling, and then using the predicted mean, we just make sure that this predicted mean will always be on our always be like kind of inside of our image space, so to speak. So as such, normally, if normally this would be a divergent sample, if we just do the step and clip, or step and project, I guess, we end up inside the image space, and like this generally tends to this generally tends to improve results. In particular, you can find many implementations of this thresholding trick in a lot of previous work. So in particular, these are some of the major GitHub repositories these major diffusion GitHub repositories. As you can clearly see, all these like clamp or all these clip to -1 to 1, and this is done after each step. And as promised, this is clearly not the correct thing to do. This is not like the right reverse diffusion process. But in practice, if we take the other like pre-existing models that we talked about previously, we apply this trick, we can actually generate samples that are of significantly higher like quality, because like this clipping can kind of combat this like divergent sampling phenomenon effectively. And we have this guide diffusion, we have these nicely generated images, we have this image gen paper, and we have like this astronaut riding a horse, and it's like a reasonably high quality image for all intents and purposes. And so there's a bit of a mismatch between like theory and practice as such, because we have this threshold of diffusion or sampling that is used in practice, which is this step project type of like system. And we also have like the whole framework set up around SDEs, but if this is not how things are done in practice, this kind of like draws a natural question: can we like make things a bit more principled? Well, one of the things that we noticed in our paper is that if we like rewrite our like if we rewrite this like step project like thresholded like sampling procedure as follows, and we take like the time step to 0, so we just take an infinite number of steps with the step project, we actually recover like a well-known process called the reflected stochastic differential equation. And this reflected SDE, we have the same like F and G, we have the same like drift and like diffusion coefficients here. And the only really real thing that we add is this DLT term. And so this DLT term effectively just constrains all of the mass. You can think about it like as a particle moving in space. It's a hard constraint. Once you hit that constraint, any outward force is instantly canceled out. And we can visualize this like pretty like straightforwardly through this following reflected stochastic differential equation called the reflected Brownian motion. It's a standard Brownian motion, but the difference here is that we will always constrain our Brownian motion to be greater than or equal to 0, because And yeah, and as such, whenever the particle hits the line, all the like downward force that would normally push it outside of zero gets canceled out, and then it just goes back inside effectively because it's a Brownian motion. And yeah. And one of the interesting things that we have with this reflective SDE interpretation is that if we take this forward reflected SDE, so this is our standard forward reflected SDE, we have a similar like reverse reflected SDE, like similar to the same coupling that we have between the forward and reverse regular SDEs. We have the same phenomenon occurring for the reflected stochastic differential equation.
Sorry.
Well, yeah.
You mind to be a bit?
Mhm.
Could you give me a bit more details on the mathematics of this? What because it's what is the stochastic process L?
Oh, this L. Okay. So back here, this
it needs
LT
to know about F, right? Otherwise, somehow it needs to correct. If F wants to push the process outside of the bound, it needs to know it for counterreacting.
The L doesn't. It doesn't. Because like at like very small time steps, basically, L doesn't really need to counteract F as much as like it doesn't. L doesn't need to know about F in particular. Like L just needs to know the position of X, and at the position of X, effectively, whenever you hit the boundary, there's like a vector force that pushes it back. Like there's like a force that pushes it back in. So like one way we can think about this is like if outside of the domain that we're working in, if there's like a bunch of if we just add a bunch of vectors that point like inside, so like you can think of like just like let's say in this case we have a bunch of vectors that we have for each like point below zero, there's a vector that points up. Basically, if we take the limit of the size of these vectors, basically it's just so that there's an infinite like force pushing upward, kind of.
Yeah, so it's like a kind of delta potential.
Oh, sorry, what?
It's a kind of delta function at the
boundary. It's exactly a delta function. Yeah.
Okay.
It's a delta function.
Yeah.
Yeah, and in this case, for the forward and reverse, basically this is just some Fokker-Planck setup. But yeah, we basically have the same exact kind of forward and reverse setup that we had previously. But the difference here is that effectively the similar thing that we have here is the score function showing up, basically. So normally we have the score function for regular reverse reflected SD, but in this case we have another score function show up for the reverse reflected SD.
So this would be. I'm sorry, I didn't get what the difference is. So isn't this the same, just the score? Or just that is with respect of the reflected forward process instead of the regular forward process?
Yes.
Okay.
Yeah.
Nice.
Yeah. Basically, effectively, like the difference here is that the score is like a bit different because the score is now like it's now on the like forward reflected process instead of the regular process, and a lot of the stuff like kind of like the score matching loss like decomposes very similarly if we want to do it this way. Everything like works because it's all like analytic effectively, so it's effectively the same derivation. But effectively we have this score matching loss function, and the only thing that changes is this term, like there's this transition kernel term here. So normally this was like a Gaussian transition. It's like this. So this is our new kernel. This is our old Gaussian kernel. So basically, if our new kernel at time, at large time steps, it goes to something like a uniform distribution, whereas the Gaussian kernel, it like will just continue going to like zero effectively. So it's effectively this like transition kernel is now different, and when we want to do our score matching loss. And so really the question, or really like one of the technical things that we need to like accomplish in order to like get this to work, is we need to find a way to like approximate our score or calculate our transition kernel effectively. Because since we're working with images which are very high dimensional, any numerical error that we or any numerical error or like numerical inefficiencies that we like observe will like just compound as we try to get this to work for like larger and larger images, basically. And so we have a couple ideas about how to compute this this transition kernel. And so one way that we can think about it is like through like this following sum over Gaussians type of like interpretation. So basically, if we have like a typical we start at this center point here, and we like take like are like, if we just run a standard, like let's say reflected SVE, basically what will end up happening is that like, you can think of it as a sum over like multiple Gaussian components, basically. So whenever you want, like whenever you hit the boundary, kind of, you enter this like mirrored state, at which point the mirrored state has like another Gaussian that like kind of like sums up back to the original Gaussian in order to get your like total Gaussian transition. So basically, like you have this kind of like sum over Gaussian type of setup. This allows you to compute the transition kernel as like basically the sum over like an infinite number of Gaussians is kind of like what you have to work with eventually. And yeah, basically we can write this out basically as follows. Your transition kernel is equal to sum over like all of the like reflected like possible images of your original like xt. You take all the like the reflected images and you sum up like the standard Gaussian together in order to get like a total your this transition kernel, like your reflected transition kernel. The interesting thing about this is that for small values of t, since sigma t will be small, you don't really have to take that many like reflected like components basically in order to get an accurate transition kernel. Yeah, effectively, yeah, basically, you know, this is because like if you imagine for this image on the left, if your like Gaussian is really small, like if your Gaussian is like really compact, really like low variance, then this like like light gray component really won't make a difference because the light gray component will be effectively 0 if it's like, you know, if our sigma or if our t is very small. That's one way. This is like one way of computing our like transition kernel. And another way of computing this transition kernel comes from like your standard mathematical setup for like bounded domains. Effectively, what we have is that for any bounded domain, we can extract like these eigenfunction or these harmonic components. So these are functions fi for which like this Laplacian, like effectively the Laplacian operator on fi, it's equal to a scaled version of fi, or according to some lambda I. And we can write this out like explicitly mathematically as follows. Effectively, so we have this transition kernel is equal to sum over like these harmonic components scaled by this like e to the power of negative lambda I sigma t squared over t. And the mathematical details are kind of a bit like deep and kind of a bit like, you know, they muddle the picture too much. But like the key insight here is that for this other like way of computing the transition kernel, if we take like a large value of t, then this sigma will be like very large. So effectively, this means that this e to the power of negative lambda I sigma by sigma, this will go to like 0 very quickly. So for large values of t, this e component goes to 0. This power component goes to 0 very quickly, and as such, we only need to take a couple of like we only need to take a couple of like of these eigenfunctions, or this summation gets truncated very fast if we have like a large value of t. And so yeah, and as an example, if we consider the unit interval, like this is how this will be the function, how the function looks like in particular. And so we can note that as k becomes very large, this gets like or as like sigma becomes very large, and this summation like converges very quickly. And yeah, so basically the idea here is that we take these two methods, this one method of like a summation over Gaussian. So we have all these reflected like images, we take like a sum over Gaussians. And that works for small t. So for small t, we just do that. And for large t's, we have this eigenfunction decomposition. And in this case, we can just do this like eigenfunction decomposition. This works well for large t's. So basically these two methods can kind of make up for each other's weakness. It allows us to compute this transition kernel very quickly and allows us to make sure it's scalable to like image size effectively, which is what like the target application for this method. So yeah, in particular, we were able to scale this up to images and how like we can generate pretty high quality samples using our method. And this is like basically in line with the samples that were observed in previous methods. In particular, one of the nice things about our like method is that when we actually scale it up to like C410, we go through the whole gauntlet, we actually end up with a slightly higher interception score than previous methods. So yeah, in previous methods, they tend to be bounded by like 10. or so. But our method for inception score, it actually goes up to 10.42, which is a nice improvement over the baseline.
Wait, what?
Yeah, sorry.
Inception should be low. Is it like?
No, inception should be FID should be low. FID should be low.
Oh, this is just the inception score. Okay, I'm sorry.
It is inception, yeah. But yeah.
So how is this computed?
The inception score is the standard. Take 50,000 images to go through a standard inception score, like inception network. Make sure that like the features match up, basically.
Okay.
Yeah.
So did you compute the FID because they are more standard in the literature?
Our FIDs were like slightly worse, but like there's a reason for why they're like slightly worse in particular. And the reason why in particular is that like for these the images that we generate, they tend to be off by like 1 to 2 pixels, or there tends to be like a 1 to 2 pixel variation in terms of like noise for all of our images. And now normally these 1 to 2 pixels type of thing is not a big deal because adversarial attacks on CFR10 go up to like 8 pixels, right? So this 1 to 2 pixels is like it's not noticeable for your average for your like human, for instance. But like FID tends to be very sensitive to like this like noise. So in particular, like previous methods for diffusion, if you don't like have your if you don't like get rid of this like 1 to 2 pixel standard deviation of noise, you end up with like FID scores which are like way worse. Like they're very inconceivably bad FID scores basically. So in general, like we don't put much emphasis on FID scores as such.
Okay, but still, the literature is the most common metric, so you need to deal with it, right?
Yeah, I mean, and this is like one of the things. I mean, our FID scores aren't like terrible per se, but it's like it's comparable with respect to like previous methods. But for inception score, which is also like this is also a big metric, we tend to like there tends to be like some give or take basically. So inception score goes up, FID scores because of this like noise issue tends to go down. Yeah. Okay, yeah, and another thing that we notice for like these diffusion guidance type of like situations is that if you try to like guide a diffusion process or a diffusion model with like effectively like with some like with something called like the diffusion guidance weight, which we haven't really talked about, but you think of it as a higher weight means a more accurate image, whereas a lower weight means like a less like class conditional like accurate image. Basically, what ends up happening is that even with a very low like amount of weight applied to a diffusion guidance system, you end up with a lot of like these divergent sampling like issues basically. So in particular, this is some previous model or one of our pre-trained models. You like run like you want to generate, let's say, a printer, and then like or some other class, and a lot of these images will blank out. And in particular, one of the things that we notice is that if we do this, like we try to do like a DDIM ODE type sampling, which is basically just an ODE version of your SD, this also ends up with a lot of like divergent samples because of like the previously discussed like the divergent sampling phenomena. No, so what we noticed also is that for even if you do apply thresholding, which is this like step project type of system, if you do apply this to your standard image generation pipeline, but with a high guidance weight, you end up with a lot of oversaturated images. And this is like one of the main issues that crops up a lot in the diffusion model literature, is this issue of like high oversaturation in images. So here we have these 4 generated images. As we can clearly see, a lot of them end up like, there tends to be this like green bleed through that happens when you try to like work with these images, and this is an issue of oversaturation. We believe that the reason why like this oversaturation exists is because you have this mismatch between the forward and reverse process. The forward is a standard diffusion process, and the reverse ends up being a reflective diffusion process because of the thresholding operator. And this mismatch, because we can like train correctly so our forward and reverse are both reflected SDEs and they match up in particular, we tend to find that this helps alleviate the problem of oversaturation. So in this case, we have this we generate the same images with the same guidance weight, but we don't end up with like this heavy oversaturation. We don't end up with this green bleed through that we had observed for in previous models.
So, but is this a problem of diffusion or it's a problem of guidance? Because it sounds natural to me that overfitting the classifier, that basically that the kind of the quirks of the classifier will cause the oversaturation, and it's more of a problem of the classifier not being perfect and the diffusion process itself.
I think there is, okay, I think the issue is more so with like the diffusion, I think, because like the issue is more so like because you have like you can imagine it like you have these, okay, so in particular for our case we're talking about classifier free diffusion guidance. So we have like 2 diffusion models instead of like it's like 1 diffusion model, 1 classifier. We have 2 diffusion models, one of them conditional, one of them not conditional. And because you're trying to add and subtract them, you can imagine that this whole like inaccurate score like phenomenon will just be like would be kind of emphasized or like or would become more prevalent because you have these 2 score models and you're trying to like sum them up together basically. So in particular, this really shows up heavily for like diffusion models in particular. And so in that case, you can think of it as it just pushes everything out of bounds, and then you end up with like the high like oversaturation. And in this case, for like this like thresholding, like this thresholding example, this is more so a phenomenon of the fact that when you threshold, you're still like kind of on the boundary of the hypercube, if you imagine it that way. So whenever you project, you're still on the boundary, and then as such, you can imagine that a lot of particles or a lot of the dimensions end up getting stuck, like let's say at the green dimension, and as such, you can't really like you just generate an eagle, but like it has to be like really green, kind of. So this is kind of the like issue that arises here. So this is kind of more of a diffusion specific thing. That being said, I think like the whole guidance, like the high diffusion guidance, and this ends up like with oversaturation, it is like kind of inevitable. And even in our models, we did see like some level of like oversaturation or some level of blurring of features. But the difference here is that we don't have the same like artifacts. We don't have the same like, well, it's this in this case, this would be like the green bleed through type of like thing.
Yeah. So to summarize, maybe my understanding is a kind of the combination of the 2 things. There is kind of a bit of overfitting of the guiding that is wants to push to extreme images that reflect the class in a kind of an exceptional amount, and that hits the wall, and then it gets stuck over the maximal saturation.
Yeah, that's a good way of putting it. Yeah.
Can I ask a bit of a stupid question? Maybe why not just using a logit transformation?
Oh yes, we tried this, or it's been tried quite a bit, and the issue with that is like, or in particular, the reason why this like is more difficult is that you end up with a lot of mass that's like too inside of the image. You're not able to get to the boundary quick enough. So for like a logit distribution, it would transform your, let's say, 0 to 1 or -1 to 1 to like -infinity to infinity. And generally for like your diffusion process, like your normal diffusion process is only gonna go to like -2 to -3 to 3, if you think about it in terms of like rule of 3 sigma. And then like this makes it like extremely difficult to go. Basically, the issue here is that you're pushing too much mass, like you're keeping the mass too far inside of your image, kind of, and this makes it like it tends to make it kind of difficult to like like do like a standard diffusion model training. And also like, and some other issues are that like we try to do it with like the logic, we try to do it with a neural, with like these standard like UNet neural operator, neural networks. It ends up being like weird things can happen. Kind of like these things were not really built for like these logic like transformations, so to speak. Yeah. And so basically have this. And another thing that we have for our method that was actually like pretty interesting is that you have this equivalent ODE that like effectively follow the same like marginal distributions as our SDE. So basically what we can do here is that we have this ODE, we take the same score function that we learned from our reflected case. And if we just we can sample like by following this ODE, this as a neural ODE, and we can effectively sample from our distribution by with this ODE. And like issue with this, or one like intuitive like problem that one might have with this setup, is that this doesn't like your ODE, like where does the reflection term go, kind of, right? One can imagine that the whole like the noise can like we can anneal the noise. This is like we can remove it. This becomes a DDIM type of sampler. But like where does the reflection term go? And actually, one of the things that like noticed is that since our probability distribution follows the following Newman boundary condition, effectively this means that like effectively this is just some like PDE boundary condition which like allows us to control our PT term. Well, actually, this means that this like gradient term or this like drift term will go to 0 at the boundary of our domain. And because of that, this means that if we actually solve the ODE, it actually is like kind of a valid diffeomorphism from your domain to itself. And as such, because of that, we can actually sample using its ODE, and this allows us to get rid of both the noise and the reflection term simultaneously, kind of. Yeah, and as promised, we can sample with the ODE. And we generate like reasonable looking samples, and these can be done much quicker because of the ODEs tend to be much quicker for sampling than SDs. So in this case, we can sample with only like around 100 steps, as opposed to standard methods, which would be around 1,000 steps. And so this is a way to bridge the gap with the previous literature. Some other stuff that we noticed was that basically more or less like our score matching loss function becomes like an elbow, basically. And as such, we can when we train with our like score matching loss, when we train with our standard training procedure, this gives us a like way to like bound the likelihoods of our data. And as such, what we end up getting is that we can end up getting pretty comparable likelihood values, in this case bits per dimension, with previous methods such as like VDM, which is like the variational diffusion models paper, and ScoreFlow, which is like I guess another type of maximum likelihood training of score-based models. So yeah, effectively we're able to get a very similar type of like bits per dimension. But one of the things that we noticed was that for these previous methods, which are relying on the OU process, these tend to like kind of require a bit with like a kind of a learned noise schedule. So you have to like either do some important sampling in order to get your noise schedule to sample correctly, or you have to learn a noise schedule outright, which is what VDM does. And this is what they need in order to get like their nicer results. But in our case, since our method, everything's like kind of unified, are the same score matching loss that we do for image quality is the same score matching loss that we can do for likelihood. We don't have to have a learn noise schedule and point sampling or anything. So effectively, we're able to do like we're able to get like close to, if not better, results than previous methods, while like having a more unified like kind of like method kind of. But yeah, the last thing I want to talk about is the fact that like our method and the way that we presented it, while we did present it like pretty heavily in the scope of like the hypercube for images, by all accounts, our method is not reliant on this like setup. So in particular, we're able to generalize our method. We're able to generalize the math to like other domains, such as let's say like a ball, a simplex, or like this like octagon, or this heart shape. And we're able to generate samples that, like in this case, a checkerboard, that are like constrained to this domain. And in particular, we're able to scale. Yeah.
So of course, I assume that in your experiment, the diffusion is pixel-wise. So each pixel is diffused independently, right?
Yeah.
Also the boundaries. So of course, in this case, you are coupling different pixels with this more complex geometries, right?
Oh, in this case, this is like 2 dimensions. So this would be a 2-dimensional sample. So this would be like, so instead of normally it would be like all the diffusion is like independent of each dimension. So -1 to 1 to the power of like however many pixel dimensions you have. But in this case, like we're talking, each of these points represents like one of the a data point in like the ball in R2.
So do you have examples where it could be useful to enforce this sort of more complex constraints?
So yeah, in particular, I think one of the things that we looked at was like simplex diffusion model or simplex diffusion modeling. I don't have the experiments like here in the presentation because like it's kind of a simple experiment, but like generally like, for the simplex in particular, we can think of like, let's say like language model class probabilities, right? So if we want to like take a language model, we have this massive simplex of all like possible tokens, kind of, and this like, so each of the positions of a language model, it's like each of the tokens, so to speak, is a point on the simplex, because each of the tokens is like kind of a probability distribution over all tokens. In this case, like we would want to enforce, instead of a hypercube constraint, you would want to enforce a simplex constraint, because we have these probabilities, and we have these we have the model over a class of probabilities instead of the class of like all images. And yeah, this was like kind of the main main research thrust, kind of, was basically like this whole idea of like high dimensional simplices. And effectively, like, okay, going back to the slide, like we can actually scale up to these high dimensional simplices, but like it's kind of like you would have to go from like your domain, in this case your omega would be like the simplex, you have to map it to like 0 to 1, or your standard unit hypercube, and then you can learn diffusion in standard unit hypercube and map back. And the reason why we have to do this is because the standard unit hypercube, we don't have this coupling of like different dimensions, and as such we're able to like do the score matching efficiently, whereas previously for the simplex, the score term would be intractable in high dimensions effectively. Sorry, the long-winded answer, I guess.
No, actually, I was wondering whether it's tractable or because you have this harmonic approach, right? But I guess you have a very large number of basis function in that situation.
I mean, even in the case where we only pick like one basis function, it's still very intractable for like high dimensions, because that would just be like the number of like kind of like a number of basis functions would have to scale like linearly at each like harmonic level with a number of like with like the dimension, kind of. But yeah, so effectively that's it. Any questions, I guess? That's it for the presentation.
I have a question. Thanks for the presentation. I was wondering how difficult is training compared to standard training, because in this case you said that we don't have a tractable approximation of the transition distribution. So how I can imagine that maybe it's more computationally expensive to train this model.
I mean, so in particular, say we have the whole so in our case, so we have the fact that this transition density is not expressible in closed form, and this is like in general one might think that this might be like crippling, but in our case we observed that we're able to compute like these transition densities like using our like two methods, this method, which is the sum over Gaussians and the eigenfunctions. We're able to compute this transition density like within machine accuracy. So let's say like 1e -9, let's say, which is like a very reasonable like approximation error. We're able to do this like pretty efficiently. So I would have to say like maybe like 6 or 7 at most. Like I'm not sure like the exact number, but something like 6 or 7 like summation terms. And generally, like there is a slight addition in terms of computational complexity, because we have to compute like 6 or 7 more. 6 or 7 more like terms, kind of. But like in practice, we observe that this isn't really a big issue for like, let's say, neural network training, because for neural network training, most of the cost actually comes from a neural network. So if let me put it this way, if the standard training time is like 1 second per iteration, our stuff is at most like 1.01 seconds or something like that. So effectively, it's the same like kind of effectively becomes like the same like cost effectively in terms of like training.
Oh, thanks. My other question is, I can see the benefit of this kind of approach, but compared to the thresholding treats they use, what would you say is the benefit? Because so what do we gain, for example, because in the thresholding approaches, like imagine they don't use a reflected forward process, and then they just use this clipping as you explained. So what do you think that what we gain of just not of doing it in this kind of quirky way of just clipping the image space at every time, compared to actually doing it properly by using the reflected forward process and the reverse forward process.
So yeah, in this case, okay, so two of the biggest like gains that we get are like most of the gains come from the fact that it's more principled theoretically. As such, we're able to like draw like a better like we're kind of able to like draw better like theoretical background in order to like justify some of these methods. We're able to like give some guarantees, for instance, on our like on our training procedure, because we're able to like make sure that all of our training data is within this compact space. So everything's like more like there's just more guarantees there. And in terms of like experimentally, I think the biggest thing that we gained, and this is back here, is this like, let's say this ODE sampling, for instance, right? So for ODE sampling, if you try to do like a guidance with an ODE sampling, because like you can't like, because for previous methods, when you try to do like an ODE sampling, you have to like, you can't do a threshold plus ODE sampling, kind of. So when you do try to do this, you end up with like images like this. And so basically ODE sampling doesn't like work as well because like you can't do like thresholding. Whereas in our case, because we're able to like kind of, because our like score function is learned properly, everything's learned properly. So when we do like take the ODE, it kind of like smushes in like the thresholding inside, or like it merges the thresholding back into the like process, the sampling for the ODE. We're actually able to like generate like samples that are like more stable, basic, or like more reasonable, much more reasonable. So in that case, like we can see that like clearly by like having like a proper score function, we're able to get like better type of like some other like better experimental like results effectively.
And I saw that in your paper you in performance hallucinating diffusion models was a bit better. So do you have any idea why is that?
For which diffusion model?
Hallucinating diffusion models, EDM.
Oh, EDM does a lot of engineering work in order to make the models the best. And also, I guess the thing with EDM though is like EDM is like very heavily engineered, in fact. So everything from like the sampler to the sampler is like, I think even in the paper for the sampler, it's not technically a like correct sample, or it's not like an SDE sampler if I remember correct. It's not a general purpose SDE sampler, so they like a lot of their stuff tends to be hyper engineered effectively. So this is like, it's kind of hard to compare with. And I guess also one of the things that EDM does in particular is they tend to focus on these like simpler test tasks, let's say C410, ImageNet 64, but they don't really have like diffusion guidance, which is, for instance, what like we need to use for like our like more like real world like use case basically. So that's like kind of the difference between the papers there.
I have another question. I don't know if someone else wants to ask. Otherwise, I will ask. With going back to the previous question about the weight in the guidance.
Yeah.
I was wondering whether just by adding the constant, because the constant basically makes more peak the conditional distribution P of y given x. So in the guidance, I think I don't know if you have the equation, the W wave.
Okay, I mean,
yeah.
I don't have the equation for like the classifier free diffusion guidance that we use for like the paper, but like yeah, sure. In this case,
so that's related to the question that Luca was asking, whether it's a problem of guidance or diffusions, because I was thinking probably just a problem of the guidance itself, because so they introduce the weight, right, to basically focus more on the mode of the class that you want to generate. So I was wondering whether this is the problem that basically produces the need of the thresholding techniques.
I think this will be like it's somewhat different for like, let's say, the thresholding technique. So for the thresholding techniques case, like clearly the mean, like let's go back to some of the mean images or the average images. So let's say we have a high guidance weight and we want to generate, let's say, an eagle. Like I don't think like this the eagle would be like green, kind of. I think this is like in this case, like most likely, from what we can tell from the Eagle case, the background should be white, I think, for the images, or blue, or something like that for the use case, and for like ImageNet. So I think this would be like, in this case, basically in the average, the thresholding, like the thresholding clearly introduces something else, but that like goes beyond like the standard like collapse that one might expect from a classifier for diffusion guidance, basically. Like, yeah, because in this case, like these images are clearly not representative of their classes. Yeah.
I mean, I think that this image is convincing. I'm a bit, yeah, it feels that the results, the quantitative results do not,
Yeah.
It feels to me that given this example, we should see that more in the quantitative results, but then those are, okay, they're fine.
But in this case, this is for CFAR. In this case, yeah, that's for CFAR, basically, yeah.
And this is the unconditional generation, right?
Oh, not conditional generation. This is the unconditional generation. Yeah, unconditional.
So I think that the most benefit is when we do conditional generation, right?
Yes, and in the conditional generation case, yeah, I mean, I think, like, in this case, like, I must admit that this high guidance weight type of example doesn't really, I mean, in practice, this is not like that big of an issue. I mean, there are cases where you have to do it for, let's say, like text to image guidance or text to image guided generation. Obviously, it's a hard experiment in terms of getting the funding and again the GPU resources required in order to replicate. So in general, like, yeah, I mean, there is kind of a disconnect here where we do see that like we can avoid some of these like issues with like threshold generation, but like qualitatively, I think it is like, it is an open question about how we have to probably optimize the model or the noise schedule, something like that, to get like better results compared for like, let's say, ImageNet class guided diffusion, in order to get better results there, and that are like strictly better, because even in our case, a lot of the images end up being like worse because of like, most likely because of the noise issue. And then also like, and there's another question also to scale it up to like text to image, which is the big use case for like diffusion guidance methods. Yeah.
So I have one point. Are you familiar with flow matching literature?
Yes.
So it sounds that the procedure will be easier from that from that literature, because in that case, instead of having a forward SD, you just have a forward kernel, which you can just set to be bounded, and you don't need to solve anything. You are free to set whatever bounded forward kernel you want, and then you can basically get the equivalent of the reverse diffusion. So
yes,
did you?
I think that's. I mean, I think, well, the biggest issue with like all that comparison would be like, in that case, you have to like get better numerical results. Kind of also, it's not really. There's a couple things. So I guess first of all, like I think for the flow matching, like FID results, flow matching like exception score results, they haven't been shown to be better than diffusion. So I mean, in this case, if you want to compare with like diffusion models, it would make the most sense to work from there. Also, I think another big like point is that like this whole like threshold mixer thing that people do in practice. This is something that's already been like, this is something that's been used already in practice for like large models. This is a core part of the ecosystem, and I think, in this case, explaining more of like why those methods like work the way they do is kind of something that people can kind of build more directly off of, kind of, right? So we have like the pre-existing method, and we need to show that this is why it works, or what's going on, kind of.
Oh yeah, I'm not complaining that you do not compare with flow matching. I think it's
I think the point was more so that like it would be easier, right?
I'm just saying that I feel that people think that flow matching and diffusion are quite different, more different than they are. That is basically the same thing with a couple of tweaks. And I feel that the literature kind of segregated between diffusion and flow matching, while basically the techniques are the same. But the big advantage of flow matching for what you want to do is that you don't need to solve anything. You just you just choose the forward kernel, and then you can use the same technique. So it does not need to be solved. And so if I were you, I would actually look into, because it could make your math quite simpler, without any need to any approximation for actually solving the equation.
Yeah. I think there's some. Yeah, I mean that makes sense.
Yeah, or I mean, I'm not an expert, so there could be something going horrendously wrong if you try.
I think the issue that would like crop up most likely is the fact that and this was in Ricky's like Riemannian flow matching paper, but like in order to like get like in order to model on manifolds with boundary, you have to constrain it such that you have to constrain the score network to have the Newman condition directly, which is a kind of which we found to be kind of difficult, and it ends up like making things a bit harder, or it makes it a bit harder to learn the network kind of. So there are some subtleties here, basically. Yeah.
Okay, so it gets easier in one side, but it gets more difficult in the other in parameterizing the network. That's what you're saying.
Yeah. It gets easier. Yeah, basically, it gets easier in doing the whole like like learning process. Yeah, I mean, and I would also say that like for most like for at least for the hypercube, it would not really be that much easier because the hypercube is already so simple in our case because our methods like are scalable in that case. But let's say if we want to do something like a simplex model, I think it would be easier to do the whole like loss function because you would just like do like the geodesic path or whatever. But the issue is more so that then you have to constrain the network to point like to go to 0 at the boundary kind of your simplex. Or yeah.
Does it need to be constrained? Will it even just learn it from the loss?
Then really bad things could happen when you sample because if you, I mean I think generally you need to constrain it. Yes, you need to constrain it, especially for high dimensional examples. You have to like constrain it explicitly.
Okay, thank you.
Yeah.
Maybe another question. I was wondering if you saw a particular behavior for different denoising steps with fast samplers. For example, I don't know how many steps do you use to generate these images, but I was thinking maybe there's a different behavior for different denoising steps.
We didn't test any of the other more fancy samplers. This was just the samplers that existed in like the pre-existing like methods, like your standard let's say your ancestral sampling plus thresholding. I think in this case, like in our case for these like images, it's like we try to for like 250, 500, 1,000, 2,000 sampling steps. It all tended to be like around the same image, kind of. It tended to be like similar, like the same issues would arise. And yeah, at least for the pre-existing methods. And for our case, yeah, we look at some other samplers, but it wasn't like that much of a foray, kind of. And it ended up being like all kind of the same.
And my last question, I promise. I was. Do you know if this same phenomenon happens in consistency models or?
I don't know. I would say that for consistency models, if I remember like the math correctly, which has been a while since I read that paper, but if I remember for the math correctly, it was effectively like they're effectively matched to like you're effectively matching like the ODE, like in terms of like one step process, one step generation, right? So you take a one step generation and you match like the ODE that would be the equivalent of like the generation. Yeah. I think the same issues can arise, I think. So for ODE sampling, let's say if you want to do a class conditional ODE sampler, if you want to like match it up together, like I'm not sure, like the same issues will definitely arise for ODE sampling, but like the question of whether or not the network could like, whether or not you can like kind of make things work is like another question. So I'm not, the best I can give you is I'm not sure.
Yeah, because I was thinking that the motivation was that basically you create a trajectory that is not the same forward trajectory and goes out of the boundaries, but with consistency models, it's just basically mapping towards the endpoint of the trajectory. So I think that, yeah, so that problem can be overpassed by just doing the mapping that they propose. But I was curious if that happened. but maybe that's not the case.
Yeah, I mean, in this case, it's just too new to see. I'm not even sure. Did they do guidance in their examples?
I'm not sure, so that's why I was wondering, but probably not. Yeah, probably it's different.
Yeah, and a lot of this stuff can like show up very subtly. So, for example, an original DDPM paper, if you try to do a sampler, like maybe like 1 out of every 10 images will like, or 1 out of every 100 images will blank out. So it's kind of not like that big of a deal, I guess. But it's one of those things that shows up.
Thanks.
Yeah.
Okay, thank you very much.
Thank you so much for having me. Yeah, it was great talking with you all.
It's a very interesting conversation. I think your work is exciting. I mean, I feel, if I have to be a bit honest, I feel that it does not convince me practically at the moment, but I think it's a very good step in the theoretical direction, because I think doing the math right is important. I believe in that. But
that's fair. Yeah.
I feel that you have to come up with a very strong practical reason for people to adopt such a more complex, because eventually it's a quite more complex math that you're asking people to use, right?
Yeah.
But great work.
Fair. Thank you. That's fair. Thank you.
All right.
Yeah.
Thank you so much. Bye-bye.
See you.